Okay, today we're going to be learning about the compartmentalization of geometric vectors. Over here we have a vector, and we can see that it's made up of a horizontal and vertical component, and that there's an angle between them. Well, we know how to operate with right angle triangles. We can say that sine theta is equal to the opposite over the adjacent, or the hypotenuse, rather. Right, and from this relation, we can say that the vertical component of any vector is just equal to the magnitude of that vector multiplied by the sine and the angle of that vector, sine theta, right? V sine theta. And we can do the same thing for the horizontal component of a vector. So let's do that. Right? We can say that the horizontal component of any vector is just equal to the magnitude of that vector multiplied by cosine theta. So we're going to see how this can be used to solve some interesting problems, particularly with regards to when you're adding vectors and finding the resultant of said vectors. So let's do that. So we have a boat over here. The wind is blowing south. The force on the sail is 200 newtons at a bearing of 100 degrees, and the force on the keel is 188 newtons at a bearing of 300 degrees. Determine the vector sum of these forces and show that the boat will move upwind. So let's do that. So a bearing of 100 degrees is about over here, which is the same as negative 10 degrees on a normal plane. And over here we have our other angle of a bearing of 300, and that's about 150 degrees this way, or 30 degrees from the horizontal. So now that we know what these angles mean in our traditional sense, let's go and solve this problem. So the beauty of compartmentalization of vectors is that the horizontal component of one vector added to the horizontal component of another vector, same thing with vertical vectors, is that they equal to the horizontal component of the resultant vector. So let's do that. Fx, horizontal component of the resultant vector, is equal to F1 cos theta plus F2 cos theta. Perfect. Let's plug that in. So our first force is obviously 200 newtons, multiplied by a cosine of negative 10 degrees, as we mentioned earlier, plus 188 newtons times a cosine of 150 degrees, as we previously mentioned how we got there. And so we get that f of x is equal to approximately, again, this is not a completely accurate number, 34.15 newtons. And it is going in the east direction as we made that our positive. So let's do the same thing for our vertical component of a resultant vector. There we go. The vertical component is just the magnitude of each force multiplied by their respective sine thetas added together. So Fy is equal to 200 sine negative 10 plus 188 sine 150. And when we add these together, we get that the horizontal component of the resultant of these vectors is approximately 59.27 newtons in the north direction, as we made that our positive. So now that we have these, we can add them to our nice little graph here, because they are perfectly horizontal and vertical. We're going to see something very cool happen. Would you look at that? We have our Fy, or we'll call this Fy, and our Fx. And this is our resultant right here. So we're going to call that R. Obviously, you have your theta right here as well. So we can see that this is a right angle triangle, and that we can use Pythagorean theorem to find the magnitude of R. So let's do that. R is equal to, oh, wrong editor. You can see that R, the magnitude of R, rather, is equal to the square root of the horizontal component of the resultant squared plus the vertical component plus the horizontal component of the resultant vector squared. And we take the square root of that, so to the 1 over 2. So let's plug in our numbers. And just pretend that there is a vector over this R right here, because I'm not able to do that normally with this editor because of the software I'm using. So let's add these together. 34.15 squared plus 59.27 squared. And we obviously can't forget to put our 1 over 2 here. So let's see what this gives us. We get that the magnitude of R, again, this is supposed to have a vector arrow over it, so just ignore that for now, I guess, is equal to approximately 68.4 newtons. So we know what our resultant vector's magnitude is. We now have to find out what its direction is. So since we have our Fy and our Fx, and we're trying to find theta, well, we can use our tangent function. And in fact, we're going to jump right to a little bit more advanced using the inverse tan function. So we know that the inverse tan of Fy over Fx will give us theta. And when we do this, we get that theta is equal to approximately 60.1. Oh, what just happened over there? 60.1. Let me just get my degree symbol over here. 60.1 degrees. Awesome. So now we have our resultant's magnitude and its direction, so we know exactly what this vector is. Pretend that there's a vector symbol here. R is equal to 68.4 newtons. And since we know this angle is theta right here, and this is east and this is north, it's 68.4 newtons east, 60.1 degrees north. Awesome. Or if we're using the bearing system, that's the same as 68.4 newtons at a bearing of 29.9 degrees. Awesome. So that's how you can use compartmentalization of vectors to solve some problems such as finding the resultant vector of two forces. Thanks for joining me, and I hope you learned something.